Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn how to characterize how sound levels change when they transmit between rooms. And we'll frame our characterization using both objective and subjective data.
So let's get started. We know all about how sound builds up and decays due to the absorption of sound in rooms. But sound transmission between rooms is another common emphasis of the design of interior acoustics. And sound transmission occurs between rooms due to both longitudinal and shear wave formation in the layers or walls that isolate a source room from a receiving room. We are familiar with longitudinal waves from before in acoustics, and these also propagate through materials. But shear waves are occurring for materials as well. So an incident acoustic field causes fluctuations of pressure on the surface of the material. Because the material supports shear, a surface wave occurs in the direction of the material, which in turn, in the source room, creates another wave. So if we have a source in one room, a listener in another, and there's a shared wall in between them, we want to find the sound pressure level. To do so, we need to quantify a power transmission coefficient, and this is equal to the transmitted acoustic power divided by the incident acoustic power. And before, we had determined this for simple material combinations, an interface. And we call this T sub capital pi is equal to AT, the area of the transmitting fluid, divided by AI, the area of the incident fluid, multiplied by R1, the acoustic impedance of the incident fluid, divided by R2, the acoustic impedance of the transmitting fluid, multiplied by complex capital T modulus squared, where complex capital T is the pressure transmission coefficient. Now, we'll simplify this quite a bit, and we'll define tau as the power transmission coefficient. It's equal to the ratio of the transmitting power, capital Pi sub lowercase t, divided by the incident power, capital Pi sub lowercase I. So we've got our layer, our incident acoustic power, capital Pi sub lowercase I, and our transmitted acoustic power, capital Pi sub lowercase t. By considering conservation of energy, the power transmission coefficient is bounded between 0 and 1. In the extremes, tau is equal to 0 is a perfectly and legitimately rigid barrier. No sound power is transmitted. In the case where the power transmission coefficient is equal to 1, this means there is no impedance difference created by the interface. This typically only occurs if the layer doesn't even exist, so that there's nothing stopping the transmitting power from being equal to the incident power. Having computed the power transmission coefficient, we then define transmission loss. It's the most common way to quantify the reduction of sound power that's transmitted through a layer. The TL, or transmission loss, is equal to 10 log 10 of 1 on tau. We also compute this as being minus 10 log 10 of tau using the power rule of logarithms. This is in units of dB, decibels. Empirical data is often used to find the transmission loss, and it takes into account the absorption of sound in the receiving room. So if we have a sound source, and in this room we create sound pressure level 1, and we measure sound pressure level 2 in the receiving room, we can compute the transmission loss. It is equal to SPL1 minus SPL2 plus a correction 10 log 10 of SW, the shared wall area, multiplied by 1 minus A bar R, which is the composite total absorption coefficient for the receiving room. This can be measured empirically as well. Absorption coefficient for receiving room divided by SR A SRR, or SR is the total surface area of the receiving room, including the shared wall. Including the shared wall. Now in practice, common walls between spaces contain multiple components. So for instance, the walls that are shown here are part drywall with standard insulation, now we imagine, as well as part windows. And we need to use a composite power transmission coefficient in this case, where tau is equal to 1 on S with an area weighted average of a sum of SI times tau I. And we'd still use our traditional transmission loss equation to compute the transmission loss for the composite wall. The area weighted average we see ends up leading to large influence by small extreme contributions. So we had the shared wall that's shown in the schematic. If one of the areas, S1, S2, or S3, had an extreme contribution from low or high values, it would lead to disproportionately great influence because transmission loss is a logarithmic quantity. So take, for instance, a perfectly rigid wall. Tau is equal to 0, and the transmission loss is infinite. But if just 10% of that wall contains an open window, the transmission loss is reduced to only 10 decibels. So going from an infinite TL to just 10 decibels is dramatic. The crack under a door is a perfect example of how a small contribution of an extreme value of power transmission coefficient can significantly influence the transmission loss of a composite wall. So let's consider a standard 7-foot tall by 3-foot wide door that in the 500 Hz octave band is measured to have a transmission loss of 29 decibels. If there's a 1/2 inch gap when that door is installed to the floor, how does that overall change the transmission loss? Well, we first need to back compute the power transmission coefficient of the door using the transmission loss equation, and we would then write 10 to the power minus 29 divided by 10. This is equal to 0.001259. The composite power transmission coefficient is then found to be the following. In the numerator, we have the area, 7 times 3 feet, multiplied by 0.001259. That is the contribution from the door itself. For the gap, we have 3 feet wide by 1/2 inch tall, which is 1/24 foot, times 1, since the power transmission coefficient of an open space is equal to 1. And then we divide by the total area. This is 7 feet plus 1/24 of a foot, multiplied by the width, 3 feet. And when we run these numbers, we find this is equal to 0.007169. Then when we compute transmission loss of the overall door, we find this to be 21 decibels. So this is a 8 dB reduction by the gap. This is a large contribution quantitatively due to a small gap below that door once it's installed. But how does this large quantitative change yield perceptive difference of the total transmission loss? The perceived loudness levels that we've seen before tell us that humans don't perceive sounds as being equal in level at different frequencies. So when we have changes of the perceived sound level, they apply whether we're inside or out. So this holds whether we're dealing with transmission between rooms or if we're making products and result in a different sound pressure level emitted from the product. So we can create a table then that compiles an extraordinarily large amount of qualitative data from many subjective user experiences to say if sound power decreases or increases by a certain amount, what is the sound pressure level change and how does a user or person perceive it to be? So if sound power changes by 1/2 or 2 times, this is equal to a plus or minus 3 decibel change in sound pressure level. People would say there's barely any difference in the sound pressure level. So we might be proud of achieving a 3 decibel change in the sound pressure level, but people would never know the difference. On the other hand, if we achieve around a 1/3 decrease or 3 times increase in sound power, this is a plus or minus 5 dB change in sound pressure level. People might notice that it's clearly noticeable there's something different about the sound level. But only once we hit a 1 on 10 or 10 times sound power change, that 10 dB sound pressure level change will be half or twice as loud, people recognizing it as being a significant change. And when we go to a 1/100th or 100 times change in sound power, there's a 20 dB change in sound pressure level, and users, consumers, and ordinary people would say that things have become much more quiet or much louder. So this tells us if in practice, in product design or product management, we need to have a significant change in the perceived sound levels of a product, there needs to be a tremendous change in the sound power radiated by that system. So let's summarize what we've learned. We've learned that sound transmission loss, TL, quantifies the capability for a layer or wall to isolate sounds from one room to enter the adjacent space. And the contribution from a portion of that layer with extremely high power transmission coefficient is disproportionately great on the overall TL. This is due to the fact that the TL is a logarithmic quantity. Significant improvements in transmission loss from a baseline design require orders of magnitude of reductions of sound power transmission.
That's it for this video. In the next video, we'll use our knowledge regarding sound absorbers and barriers to gain new intuition for how to compose materials that best contain sound.